This is the last chapter that'll be covered on Exam 3, Chapter 8, and the topic is solutions. So I'm going to share the PowerPoint. And there we go. And then we'll turn that into a slideshow. There we go. Okay. So solutions. Those are the topics, and they're just there for general information. We'll get to them one at a time. So by definition, a solution is a homogeneous mixture of two or more substances, with each substance still retaining its chemical identity. So when a solution forms, technically speaking, there is a reaction of sorts, because you do get exchange of forces, but you don't get a change of chemical identity of any of the components of a solution. Now, of course, homogeneous means the same everywhere, which means that any place you look at that solution in any position, three-dimensional position, take a sample for instance, the composition will be the same. That is, you'll have the same amounts of all the substances, relative amounts, percentage composition will be the same no matter where you look. Now, these solutions, we typically think of solutions as a solid dissolved in a liquid, like salt water or sugar water. But that's only one type of solution. In chemical terms, a solution could be any mixtures of starting phases. Alcoholic beverages are solutions of a liquid in a liquid. You can have gas solutions. A gas dissolved in water is a starting place for pop. If you just have gas, carbon dioxide in water, then you've got club soda, I think. I tried it once, but it was horrible. Anyway, gases can be dissolved in liquids. Gases dissolved in gases are a solution. The air we breathe is a solution of primarily nitrogen and oxygen and some argon, and trace amounts of carbon dioxide, water vapor, various other molecules. You can even have a solution of solids in solids. Brass is an example. Brass is a solution of primarily copper and nickel. You can modify its behavior. This is also called an alloy, but it's technically a solution. You can put other things in there, but the major components are copper and nickel. Etc. What do I mean by that? There are different possibilities. Let's see if I've covered everything. Gases and gases, solid solids, liquid liquids, gas and liquid, gas and liquid, gas and gas, gas and solids. You can have gas. You can have gases dissolved in solids. I'm trying to think of an example. Oh, catalytic converter. In your car has beads. Ceramic, well, they used to have. I think different engineering possibilities are now. But it used to be you had these ceramic beads, and they were coated with platinum and palladium. So there's your solid. Platinum, palladium. And what they would do would, the gases as they pass over them would dissolve into the platinum and palladium, and it would facilitate the reaction. They're called catalysts. They make the reaction go faster. So that converts the unburned products of internal combustion engine into more harmless components. Let's see, what else am I missing? Liquids and solids. You can get liquids dissolved in solids too, although I can't think of an example right now offhand. All these combinations are possible, and they make solutions, homogeneous mixtures. Now, a homogeneous mixture, by definition, is a solution, but at the end of this chapter, we're going to look at another type of mixture that behaves like a solution, but it's not a solution. So that's sort of a teaser. We'll get to it. So, by definition, a solution is composed of at least two components. One solvent and at least one solute, one or more solutes. You can only have one solvent, but you can have lots of different solutes. And in general, the largest component in that solution is the solvent, and the minor components are the solutes. There are exceptions, and sugar water is one. When you put sucrose into water, you usually start off with a large amount of water and you start adding your sugar. Like you're making hummingbird feeder juice. You start off with a small amount of sucrose, which makes it the solute, and water's the solvent. But if you keep adding sucrose, if you keep adding table sugar, you'll eventually reach a point where the amount of sucrose exceeds the amount of water. It's just the nature of the solution. We still call the sucrose the solute because it started out as a minor component. But you can have large, enormous amounts of sucrose dissolved in water. In fact, the industries that use a lot of sucrose in their manufacturing processes often have the sucrose shipped in as a solution, a highly concentrated solution. Because it's easier to move around. Pumping something is a lot easier than moving solids. Okay, so that's the definition of a solution and its components. Here's an example. Right, so you have water and you add this solid to it, and it goes into solution. It's completely evenly distributed throughout. And this particular solute changed the color of the water. Okay, this is sort of a rehash and maybe some additional terms for the properties of solutions. You got to have two components, one solvent and at least one solute, but you can have more solutes. Now, the overall composition for the solution can be changed if you add more solute. Right, so you have a certain amount of solute dissolved in this beaker, and if you add more, that'll change the composition. Right? It has a certain percentage of the solute dissolved in the solvent. The properties of the solution can change, often do change, as if you change the ratio of solute to solvent. And we'll talk about some of those at the end of the chapter. Now, it says properties change. Most of those properties that change are physical properties. The chemical properties are still based upon the identity of the solvent and the solute. So they generally are only slightly modified, if at all. The solutes that go into solution exist as individual particles at the smallest possible dimensions. So if we dissolve, if we're making pop, we'll dissolve carbon dioxide in water. So the carbon dioxide molecules remain intact in water. They're no longer gases. They're in solution, but the individual molecules remain intact. Other examples, if we try to dissolve, let me think of something. How about, well, the only individual atoms I can think of are the noble gases. The noble gases would remain as individual atoms, like helium. But if you try to dissolve an ionic solid in water, assuming it goes into solution, then you won't have the ionic solid like this. You'll actually have individual ions in solution that break apart. That's characteristic of ionic solids that go into solution. They break apart into individual ions. And that's important to recognize because of the effect that the concentration, you can think of the concentration of sodium chloride in aqueous solution as a certain percentage, but since it splits into sodium and chlorine, the concentration of the ions then would be doubled. And we'll talk about that also in just a few minutes. The solutes will never settle out. A true solution remains a solution forever, as long as you don't change the composition. For instance, evaporate the water. Of course, if you evaporate the water of a sodium chloride solution, the sodium chloride is reclaimed by physical means. Doesn't take any chemistry. And if we put sodium chloride in solution, we have suffixes that we use to describe. This would be sodium chloride crystals, like in your shaker. This would be sodium chloride in aqueous solution, AQ. That's just to be clear on what form the sodium chloride is if we want to put it in a chemical reaction. Okay, so this is just a test. In a homogeneous mixture containing 80 milliliters of water and 20 milliliters of alcohol, which one's the solvent, which one's the solute? The solvent would be water and the solute would be alcohol. Okay, another term, solubility. What do we mean by solubility? The solubility of a solute. We always talk about solubility in terms of the solute, and then we add the solvent as an additional term. But the solubility is in terms of the solute. And that is the maximum amount of solute that we can dissolve in the solvent. There is a limit. Even sugar dissolved in water has a limit. Sodium chloride, table salt, has a limit as to how much you can put in solution. And that's called its solubility. Very often it's expressed, if you look it up, the value for the solubility of a substance, if you look it up in a reference manual like CRC handbook. It will usually give the solubility in terms of grams per 100 milliliters. Okay, so how many grams of the solute will go into 100 milliliters of solution? And it will specify a temperature. Sometimes it says 0 degrees. Sometimes it says 20 degrees. And sometimes it'll say insoluble. We'll talk about that also in just a few minutes. So, environmental conditions influence that solubility, how much will go into solution. Temperature is the primary focus for solubility. For solids, and now we're going to focus on solubility in aqueous solutions, in water, as the solvent. Most solids are more soluble. In other words, you can put more solute in water if the temperature increases. And that's the case for most solids that do go into solution. Of course, if it doesn't go into solution at all, that's a moot point. It doesn't matter what you do with the temperature. Although some solids that are insoluble at low temperature become soluble at high temperature. Now, there are a few exceptions in which their solubility increases as you decrease the temperature. But for most solids, they become more soluble as the temperature increases. Gases are just the opposite. Gases become more soluble as you decrease the temperature of water. So when you heat water on the stove, you're going to boil water to maybe cook pasta. As you heat the water, what happens first? Before you get to the point where you know it's a rolling boil, before that point, you start getting these little tiny bubbles, and they might cling to the edge of the container like that. That's not water. Those bubbles, that's not water boiling. Those are dissolved gases coming out of solution. As we increase the temperature of the water, we degas it. Dissolved gases become less soluble, so they form gases and they float to the top and they're gone. So right before water starts to boil, these should all disappear. And then you start to produce water vapor as your gas. So at that point, you could seal the vessel, pour the water into a vessel and seal it, and then you would have degassed water, if that's what you wanted. Now in the chemistry laboratory, very often that's what you want. Not just water, but any of your solvents. Sometimes you want them to be devoid of gas. Okay, so that's the effect of temperature on solubility. These are examples. We just say, here's lead 2 bromide. Increase the temperature from 0 to 100 degrees, and you increase its solubility by a factor of 10. And this is in terms of grams of solute per gram, 100 grams of water. So the expression of solubility can change, and it needs to be explicitly defined. What do they mean by these numbers? What are the units of measure? That's extremely important. And each one of these is more soluble as you increase the temperature, although the degree of solubility is different for each one. Like lead 2 bromide from 0 to 100 increases tenfold. But silver sulfate only increases by about 3, a factor of 3. So you do get those differences in solubility with temperature. Here's an example, calcium acetate, right? So you remember what the acetate ion is. Right? That's the acetate, polyatomic ion. Combine it with calcium, which has a 2+ charge. Now you need 2 of these. That's your calcium acetate. It becomes less soluble as the temperature increases, so conversely, it becomes more soluble as the temperature decreases. We don't have a really good reason for that happening. We have some explanations, but what I mean by reasoning is we don't have a model, a mathematical or a physical model that will explain why this happens in certain compounds and not in others. Which probably means there's some poor graduate student somewhere working on the problem for his dissertation. Okay, how about the effect? We talked about temperature. Now, how about the effect of solubility, effect of pressure on solubility? Well, you can pretty much ignore the effect of pressure on solids and liquids and their solubility in water. See, we're kind of drifting toward aqueous solutions only. And that's understandable because most of the important solutions that we're interested in are where solvent is water. So we're going to tend to focus on that unless I explicitly mention non-aqueous solutions. But for this situation, as you increase the pressure on solid solutes and liquid solutes, there is virtually no effect of pressure on solids and liquids dissolving their solubility, that is, in water. Whereas the solubility of gases are, for each gas, is affected dramatically by an increase in pressure. And in fact, there's a law that goes with it. It's called Henry's law. So Henry's law says that the concentration of the gas in solution increases as the pressure increases. Right? So they're directly proportional. Concentration equals, well, I'll use the same notation they use. That's a constant value, right? Constant. And this is the partial pressure of the gas on that the partial pressure of the gas as it's sitting above the solvent, right? So we have a gas up here, we have a piston. So if you push on that piston, you get more gas dissolved in the water. And it's directly related to the pressure. Only we need this constant, Henry's constant, in order to determine that. So, let's see. I got to refresh my memory just for a second here. Before I go off on a tangent. Yeah, okay. So recall that when we talked about the gas laws, we said that like Boyle's law was P times V equals a constant. So we transformed that into before and after, right? And I showed you how that happens. We can do the same thing for Henry's law. So if we combine these terms so that the constant is on one side, we have concentration divided by pressure equals Henry's constant. Well, if you do something to the gas, if you change the pressure, then you get the pressure increases, and of course the concentration increases, but they're still both equal to Henry's constant. So that means we can get rid of the constant and now these two expressions are also equal. So you really don't need Henry's constant if you're in a situation where you're measuring concentration and pressure before, and then one of the terms after, you can solve for the unknown. Okay, some more terms. So when you reach the solubility of your solute in the solvent, we say the solution is saturated. It has as much solute as the solvent will hold, and no more. So how do you prepare a saturated solution? The quickest way for those solids that are more soluble with higher temperature is just to heat your solvent. And you have beforehand, you have calculated how much, because you know the solubility, you've looked it up in the manual, so many grams per 100 milliliters. So you know with a certain amount of solvent, how many grams of your solute should be soluble in that solvent. And then you add some more. You want a little bit of excess. So then you heat your solvent to make the solute more soluble and dissolve it. And then you cap your vessel and you let it sit and let it cool. And as it cools, it may undergo a process that produces a, let's see if it's on the next slide, a supersaturated solution. That is, it's got more solute in it than it's supposed to have at that temperature. But this is a very unstable situation. All you have to do is agitate it or reach in with a stir bar, a spatula, or you may just go in and scratch the inside of your container and produce irregularities that promote precipitation. So if you do that, and once it reaches room temperature, and you've got crystals of the solid settled on the bottom of your vessel, then you know that your solution is saturated. And you can mix it up if you want to and let it settle again. Then you're absolutely certain that you have a saturated solution. Then what do? Well, if your solution is going to stay at that temperature forever, then you can filter it and just remove all the solids. Or you can just leave the solids in there. So then if the temperature goes up or down a little bit, then the saturation will remain because you have a little bit of solid down there that will either collect more solid as the temperature drops or dissolve more solid as the temperature increases. Then no matter what temperature you're at, you have a saturated solution. Okay, like I said, supersaturated solutions are unstable. All you have to do is agitate them and the dissolved solid will precipitate. Anything that's less than saturated is called unsaturated. So that's a fairly simple definition. Most solutions are unsaturated, but we also have other terms for them. If they're close to the saturation point, we say they're concentrated. They haven't reached saturation yet, but they're concentrated. If they're way, 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 way far away from the solubility limit, then we say they're dilute. And these are qualitative expressions. The only one that's quantitative is solubility. When you say solubility, then that means you have a number to go with it. So what happens here if you have one solution here that's has a certain amount of this blue chemical in it? It's probably copper sulfate or copper chloride. If you let the water evaporate, what happens? The solute becomes more concentrated as long as the solute is not volatile. If the solute will not evaporate at these temperatures, and that's most ionic solids, then as you evaporate the water, you concentrate the solution. And you can see it here with the change in color. You get a deeper blue. Because you got the same amount of solute, but less volume. It's more concentrated. Okay. I mentioned this earlier. Aqueous solutions are where situations where water is the solvent. Non-aqueous solutions where you don't have any water and something else besides water is the solvent. These types of solutions are useful to a limited extent in inorganic chemistry. But organic chemistry, when you're talking about carbon-based molecules and various types of reactions that you want to accomplish, non-aqueous solutions become very important. For the obvious reason that if water is there, then it can also be a reactant in your chemistry. If you don't want water to react, you want a different reaction to occur, then you need a different solvent. So those non-aqueous solutions are important for, especially for organic chemistry. Okay, how does the temperature and pressure affect the solubility of gas in water? Increasing the temperature decreases the solubility. Increasing the pressure increases the solubility, according to Henry's law. Okay. So now we're going to look at the theoretical basis for dissolution of a solute into a solvent. And we can visualize this as occurring in 3 steps. Step 1. Okay. Solute molecules are separated. And in order to do that, because the solute molecules are attracting one another, this takes energy. This is endothermic. You have to put energy in. Okay? The other step that has to occur is solvent molecules are separated. So the bonds that hold the solvent molecules together have to be broken. Not the internal bonds of the molecule itself. Like you don't break the water molecule into hydrogen and oxygen. You break the intermolecular forces that are holding the water molecules together. This is also endothermic. You have to add energy to do that. The third step is where the solute molecules and the solvent molecules form bonds. Now these are not what we would call they're not ionic bonds, they're not covalent bonds. They're intermolecular interactions that allow the solute to remain in the solvent permanently. That's why they don't settle out, because these interactions occur. And this is exothermic. So you put energy in here, put energy in here, you get some of it back. Okay? That's a three-step model for the formation of a solution. Now, we all know, especially in the medical situation, in the hospital or in emergency vehicles, you have hot packs and cold packs. And they're these bags filled with water, and they have a little capsule of some kind inside that separates a compound from the water. You activate them by breaking that packet inside and mixing it. When you do, a hot pack gets hot, a cold pack gets cold. So they're two different chemicals that are dissolving in water. The hot pack gets hot because you put energy in here and here, but you get a whole lot more energy back. If the heat of 3, and we express that this way, of 3 is greater than the heat of 1 plus the heat of 2, then you get a hot pack. If it's the other way around, if you have to put more energy in than you get back, then the pack gets cold. Okay? So this doesn't happen instantly, right? It's a measured rate of dissolution. Well, what factors affect the rate of that solution formation? Since this is a physical process, we're interested in physical properties, physical factors that affect the rate of solution. The most obvious one is the particle size. If you start off with smaller particles, you're going to get solution formation quicker. So if you take a big chunk of rock salt and drop it in water, versus a teaspoon of granulated salt in solution, which one's going to go faster? The granulated, of course. I mean, even if you mix them up, granulated one's going to dissolve faster. There's more surface area. And this 1, 2, 3 step process occurs at the surface of the solute. Okay. I just mentioned the second one, agitation. You can increase the rate of dissolution by agitating. Right? So that's why when I'm in the lab, when I was in research, to form a solution, I would put my container on a stirrer, a machine that you can control the rate of stirring, and the connection would be magnetic. I would put a little bar in there that had a magnet in it, and it's coated in Teflon, and put it in my liquid. And magnetic locking between, excuse me, the magnetic coupling that occurred between the stir machine and the stir bar would maintain that agitation. That way I don't need 3 or 4 hands, and I can do something else while it's stirring. And then as you add your solute, that agitation is maintained. You can also change the rate of solution by changing the temperature. In most cases, for solids, increasing the temperature will increase the rate at which the solution is formed, with some exceptions. With gases, you can get gases into solution quicker by cooling them down. So when I buy a bottle of pop, a 2-liter bottle of pop, I don't open it immediately. I don't let it sit on the floor and open it when I want to drink. I stick it in my refrigerator. I put it in the refrigerator because if it cools down, then more gas is dissolved in the liquid, and when you open the cap, you don't get the big pop that you would at room temperature, which means the gas is still in the liquid. And the carbonation of your beverage is part of the whole point of a carbonated beverage. It's the combination of carbonation and sugar, which is basically sweet sour, in addition to other components, of course. That is the pleasurable part of drinking pop. And that's a temperature effect. Okay. The last effect that influences solubility is one we haven't mentioned yet. It's called the common ion effect. So I'm going to use Le Chatelier's principle. So let's say we have sodium chloride, solid, and it's going into solution as sodium ions and chloride ions. Okay? Now, let's, for argument's sake, say we've reached equilibrium. That is, where we've reached the saturation point. You still have some solid in there, but you also have the ions in solution. Right? We have a saturated solution. Now, what would happen if we add chloride ions to that solution? Say hydrochloric acid. You just add some hydrochloric acid. Or you could add another salt like potassium chloride. We want to get chloride in there. So what would happen if you add chloride? The equilibrium would shift that way to consume some of those chloride ions. Well, the same concept is useful if you're trying to dissolve sodium chloride and you've already got, let's say it's an acidic solution, you've already got hydrogen and chloride ions in solution, and you're trying to put sodium chloride in solution. So you've got these chlorides already there, right? So this salt its solubility will be reduced because there are already chlorides there that are resisting the dissolution. In other words, you try to put chlorides over here, but that increases them in Le Chatelier's terms and drives the reaction back this way. So when you have a common ion in solution, this would happen with sodiums too. If you have sodium ions, the same thing. If you have a common ion already in the solvent, then the solubility of the compound is decreased. That's the common ion effect. Okay. So we need to get a better grasp on solubility. Generally speaking, and I've always heard this expressed this way, like dissolves like. So what do we mean by like dissolves like? Well, it's not one gender dissolves another gender. What we're talking about here is polarity. The polarity of the solvent versus the polarity of the solute. If the solute and the solvent are both polar, then they are more likely to be soluble. The solubility is there. That's one rule. If, however, the solvent and the solute are different, well, before I do that, let's say they're both nonpolar solvents. If the solute is nonpolar and the solvent is nonpolar, then they will become soluble. The solubility will be there also. But if there's a difference, if one is polar and the other is nonpolar, then they will not mix. Perfect example, salad dressing. If you make your own salad dressing, you're going to combine vinegar and oil, usually olive oil. Doesn't have to be, but it can be. And then some spices. And you put them in a vessel, sometimes a vessel that's made especially for that, and sometimes you do like I do and just use what you have at hand. I like those little sliced chipped beef containers, about that big. They have a snap-on blue cap made by Armor. And once you use them, you just wash them out and keep them around. And you can put your oil and vinegar in there with spices. Mrs. Dash is a good one. And then cap it and then shake it like crazy. And it mixes temporarily. Right? And you pour it on your salad. That's just the right size for one salad. So you pour it on your salad before they separate. You know they're going to separate. Water is a polar solvent. Oil is a non-polar solute. They don't mix. You can shake them up, and what that does is it breaks the particles up, the oil globules, into smaller pieces. So they're sort of mixed, but they're not uniform. Now that's in general terms. Like dissolves like. But there are some cases where the ionic solid will not remain soluble in water. These are insolubles. Now, how do we determine that? Well, there's a set of rules that you can go by, but I would only require my classes to memorize those if they were going to make a career in chemistry. Then those rules would really come in handy. But for our purposes, I've got a chart. And I'll show you how it's arranged in just a second. In fact, let me do that one first and we'll come back. So I'm going to skip these slides. And there's the table. So notice across the top you have cations. These are most of the common cations. Metal ions, most of them, except for ammonium here. And then down the left-hand side are anions. Most of these are polyatomics. Not all of them, but most of them. Right? There's some halogens right here. There's oxygen, there's sulfide, but the rest are polyatomics. Now, how do you tell if a mixture containing one of these cations and one of these anions will be soluble in aqueous solution? And that's what this is all about. This is only aqueous solution here. You just do like you would reading a road map, right? You want to go from Beckley to Charleston. You just read your road map. You find Charleston on one side and Beckley on the other, and you follow them down until they meet, and it tells you how many miles. In this case, you follow them until they meet, and it tells you whether they're soluble or not. If it's grayed out, then they're considered insoluble. If it's non-grayed, then they're soluble in aqueous solution. Now, there are a couple of exceptions, right? And they're listed down here. Calcium and strontium hydroxide, see calcium there, hydroxide, is slightly soluble. So it would form a dilute solution of calcium hydroxide. Strontium hydroxide, same way. Magnesium sulfide doesn't exist because it decomposes in water. Right? So that would be an invalid compound altogether. And the ones with 3 asterisks are those metals that combine with oxygen. And what they do is, rather than be stable metal oxides in water, they react with water. There's that reaction with water again. And they form hydroxides. Right? So those are the exceptions. The rest of them are either soluble or insoluble. And if you have this chart, and you do have this chart, that's available in your useful information in the folder containing the exam. So all you have to do is be sure and print it out before you use Lockdown Browser. So once you go into Lockdown Browser, you don't have access to anything but the exam. So you need to go in there with your browser, not Lockdown, but the other browser, and print off copies of these things that are allowable in that exam folder and have them with you. Periodic table, the solubility rules, there may be others. Just print them out. You'll have them with you when you go into Lockdown Browser. Okay, let's go back to the rules. Okay, this is the way the rules are listed in your textbook, but I like the set of rules in this form better. The reason, notice they're numbered 1 through 7. The reason I like this better is these groups of compounds that are formed are in order from 1 through 7. If you have a compound that can be identified in terms of one of these rules, more than one of these rules, then the one with the smaller value wins. In other words, if you have one that is satisfied by rule 4 and rule 1, then rule 1 wins. So if rule 4 says it's insoluble, rule 1 says it's soluble, then it's soluble. Okay, that's the value of this format. Okay, this group, these elements, all these alkali metals form soluble compounds with no exceptions. So these metal cations combined with any anion will form a soluble compound. And the same thing for ammonium. The ammonium as a cation will form soluble compounds with any other anions. Okay, and the list goes down. Nitrates are all soluble. Right. Chlorides, all chlorides, all bromides, all iodides, all these halogens, these 3 halogens are soluble except for these 3. Silver +1, lead +2, and mercury oxidation state 1. Remember mercury? I'll refresh your memory. Mercury always has a 2+ charge. So if there's only one mercury, that has an oxidation state of 2+. But if there happen to be 2 mercuries, each one is an oxidation state of 1+. Okay, so this mercury is a 1+ oxidation state, but it forms an insoluble compound with any of these halogens, as does silver and lead 2+. Okay, so you'll notice as we get lower and lower, or higher number in this set, we've run across more exceptions. Okay, carbonates, chromates, phosphates, and sulfites. Remember, SO3, 2-, not sulfate, sulfite. These form insoluble compounds with cations, except for group 1. See? So if you have a compound that looks like it's insoluble with group 4, but the cation is rule number 1, then it's soluble. Okay? So lithium carbonate would be soluble. Potassium chromate would be soluble. But calcium carbonate would be insoluble. Okay? And there are more rules. Since you don't have to memorize them, I'm not going to spend any more time on them. In fact, the more you do chemistry and the more you use that table, these rules will sort of become ingrained. You'll recognize whether compounds are soluble or insoluble the more you do them. So practice, practice, practice is best. All right. So the greater the difference in solute-solvent polarity results in less solubility. So when we talked about like dissolves like, we were sort of absolutes at opposite ends of the spectrum, right? If one is polar and the other is nonpolar, they won't dissolve. But as you get closer together in polarity and nonpolarity, as they get closer together, the solubility increases. So solubility is on a continuum, so to speak. Which of the following ions are generally soluble in water, form compounds with lead 2+. Right? We know lead 2+ is insoluble as a chloride. Right? You just look at the table. Lead 2+. Here it is right here. Right? The only one that is soluble, and this is a better way since most of them are insoluble, look at the soluble ones. Nitrate, right? Nitrate's over here. Nitrate, chlorate, perchlorate, and acetate. Those are the only ones on this list that are soluble. So we can go back to our problem and say, all right, that's insoluble, that's insoluble, that's insoluble. Nitrate's the only soluble one. And sodium is just ludicrous, right? You don't form ionic compounds between two cations. So that's why nitrate is the only soluble compound that will form out of this group with lead 2+. Okay, so when we got a solution that's up to the point of saturation, we need a way to quantitatively express its concentration. How much solute is dissolved in that solution? And there are several ways to do it. The simplest way is by percent, although it has its pitfalls. Right? We'll talk about it. And here's an illustration. This is the Achilles heel of percent. Percent is a dimensionless number. That means parts per 100 parts. So what's a part? Right? Parts cancel. Parts on top cancel parts on the bottom. It's a dimensionless number. So we need to know what the parts are, right? Well, what is the part? Well, if it's a mass of solute in mass of solution, then it's grams per 100 grams. So that would be mass-mass expression. Percent mass would be, it could be grams per 100 grams, or it could be kilograms per 100 kilograms. Any expression of mass in those terms, and that has to be equal to that, and that has to be equal to that, parts per 100, that's mass percent. How would you calculate it? Well, you have the mass of the solute divided by the mass of the solute plus the mass of the solvent times 100. That's how you get it. Because if you only have this one divided by this one, which is the total mass of the solution, that's a fraction. You only get a fraction there. If you want parts per 100, you have to multiply it by 100. Okay, that's mass percent. What about mass or volume percent? Then you need to change your units to volume. Right? So this one, let's get rid of that one. This one could be something like milliliters per 100 milliliters. Or liters per 100 liters. Whatever the volume is. That would be volume. And in that case, you would change this to volume. Okay? Or you could do combinations. You could have, one more common one is mass volume. Now it becomes tricky. Right? How do you relate mass and volume? Well, the mass of the solute, well, what's the volume of the solute? You don't know. Not really. You might know the volume of the solvent, but this has to be measured as the volume of the solution. That's where it becomes tricky, because even if you know what the volume of your solute is, when you put them together, the volume of the solution may not be the arithmetic sum of the two volumes. Why? Remember that scenario where we have the 1, 2, 3 steps, right? The first step where you break apart the solute. Second step where you break apart the solvent, sometimes called make a hole. Make a hole for your solute to go into. Well, when they combine one another, their total volumes might be completely different because of their interactions. In other words, the solute might fit into spaces that were there before, or have been slightly expanded to accommodate the solute, in which case the total volume would be less than the arithmetic combination. Okay, so that's the problem with percent. Whenever you see percent composition, it better be specified. What type of percent is it? What are the units? Are they mass or volume? All right, let's see. Let's scoot this back over a little bit. There we go. I showed you this one before. The mass of the solute divided by the mass of the solution times 100. And don't forget to include the mass of the solute in your calculations for the mass of the solution. You have to add that in there. It's both in the numerator and in the denominator when you do mass percent. So in this case, what's the percent by mass of glucose in a solution where you dissolve 5.5 grams of glucose in 78.2 grams of water? Well, 5.5 goes on top, and 78.2 plus 5.5 goes on the bottom, times 100, and that gives you 6.6%. How about volume? Where do we use volume? One common use of volume is in the strength of alcoholic beverages. Right? If you look on the side of a bottle of wine, for instance, it might say 15% ABV. 15% alcohol by volume, which means 15 milliliters of alcohol in 100 milliliters of solution. So here's a case. We're using methyl alcohol in this one because we don't want anybody to drink the slide. Ethyl alcohol is the drinking kind. Methyl alcohol is wood alcohol. And it's the kind, if you drink it, will, besides making you drunk, of course, it'll make you go blind. And if you get enough of it, it'll kill you. So let's say we have 30 milliliters of methyl alcohol in enough water to give you 435 milliliters of solution. Okay. So you have 30 milliliters of methanol, which is written like this, divided by the total solution. And we're given that, 435 milliliters of solution times 100. So what would that be? Let's see. So we have 30 in the numerator. We have 435 in the denominator times 100. That's 6.3 positions, 3 significant figures. 6.90. Percent volume, or ABV, alcohol by volume. Okay? Let's see, how am I doing on time? Okay, I got about 45 minutes left. Let me see, I better get a move on here. Mass volume. Mass of the solute volume of the solution. Okay? For sodium chloride, in this case, say 15% mass solution of sodium chloride means 15 grams of sodium chloride per 100 grams of solution. Our 6% methanol solution is 6 milliliters per 100 milliliters of solution. And notice we have a conversion factor. This is 6 milliliters of methanol in 100 milliliters of solution. So if you have say 200 milliliters of solution, and you want to find out how much methanol is in that solution, you have 6 milliliters of methanol. That's another way to abbreviate methanol, per 100 milliliters of solution. And notice solution cancels. So now we have 6 times 200 is, that's 1200 divided by 100 equals 12 milliliters of methanol. So you can use these values as conversion factors. Let's see, mass percent concentration of 10% has to be grams per 100 grams. So that's 10 grams of solute per 100 grams of solution. Oh, excuse me. No, I was wrong. It's 90 grams of solvent because the total has to be 100 grams. I misread that. If that had been solution, I would have been okay. But 100 grams of solvent is not right. 10 grams of solute and 90 grams of solvent will give you a 10% mass solution. How many grams of sodium chloride are needed to prepare 150 milliliters of 0.9% mass volume sodium chloride? All right, so here we want to end up with 0.9%. 0.9% mass volume sodium chloride. Okay, so the question is, how many grams of sodium chloride do we need? Well, if we're going to have this, what does that mean? That means 0.9 grams per 100 milliliters of solution. Okay? 150 milliliters of solution multiplied by that will cancel this one and leave us with our answer, 0.9 times 150. And see, I've already included the 100 factor, the percent factor in there. 0.9 100 by 150 times 1.35 grams. 1.35 grams of sodium chloride. Okay? Now, in chemistry, this expression of concentration is much more useful. Molarity. And the reason it's more useful is because if you're talking about a chemical reaction, remember what I've always said about chemical reactions. If you have a balanced equation and you need to find out something about another part of that equation, I think I've said that. Hold on a second. I want to be sure we've discussed this in past chapters. No, we haven't. Measurements, atomic structure, bonding, chemical calculations, formulas, mass, moles, and chemical equations. We have talked about it. I'm sorry. Refresh my memory. You can't go anywhere in that balanced equation unless you have moles. So molarity, if you're reacting liquids with aqueous solutions of some compounds reacting together, then molarity is a much more useful expression of concentration because that's easier to convert and find the number of moles of reactants to produce products. So molarity is much more useful. And molarity is defined as the number of moles per unit volume, right? This is my abbreviation for moles, my symbol for moles, and this volume has to be in liters. When you do that calculation, if you have moles and liters, you can calculate molarity. If you have moles and milliliters, you got to convert the milliliters to liters before you can do the calculation. Okay, so there's the definition of molarity, and here's a problem. You have 1 mole of sugar in 125 milliliters of solution. That's important. It's not solvent, it's solution. 125 milliliters of solution, right? So how do we do the calculation? Well, we've got the moles. How about the volume? 125 milliliters is how many liters? It's 0.125 liters. Okay? So I get 8 molar. 1, 2, 3. That solution is 8 molar in sucrose, in sugar. Okay, how did I know to do that? Well, you can do it by dimensional analysis. You can say 125 milliliters, and we want to convert that to liters. So we need to cancel milliliters and leave us with liters, right? There, there. So how many milliliters in a liter? 1,000. Divide 1,000 into this. There you go. So I did that by simply moving the decimal place 3 places to the left. Tens, hundreds, thousands. A way to check yourself to be sure you're doing it in the right direction is to remember the rule. If the unit of measure gets bigger, then the number gets smaller. So we went from milliliters to liters. The unit got bigger from milliliter to liters. Big liters, milliliters, liters. So the number has to get smaller, 125 to 0.125. So that's sort of a check on yourself. All right. Now, well, there's the calculation and the answer. You can use this formula, the formula for molarity. If you know 2 of those values, you can solve for the third one. It's like any algebraic expression, right? So in this case, we know the molarity, right? We know this one. And we want to obtain 2 moles of sugar. So we got that one. We want to know the volume. So solve for volume, right? This one goes here, that one goes there. And then plug in the values, right? 2 moles. And molarity is 10. Right? So that equals 2/10, 1/5, 0.2. 3 places. Liters. We need that many liters of solution. And once we have that many liters of solution, we know we have in our possession 2 moles of sugar with a 10 molar concentration. Okay? How many milliliters would that be? Just curious. Liters to milliliters. The units are getting smaller, right? So the number has to get bigger. 200 milliliters. Okay. The reason I made that point is most laboratory glassware is calibrated in milliliters. So even though you do the calculation, you know, how can you measure it? You need to go by milliliters. Okay. So in this problem, the point of this exercise is to illustrate that molarity of a solution, if you have 2 different compounds with exactly the same mass of the compounds, and they're going into exactly the same amount of solution, you will have different molarities. Well, with one exception. If both of these compounds had the exact same molar mass, then they would have the same molarity. But in this case, they don't. So we have 100 grams of each. We can't calculate molarity with grams. We need moles, right? So that means we have to calculate the moles of each one based on their molar mass. So for sodium hydroxide, let's see, I need another marker. For sodium hydroxide versus potassium chloride, the molar mass of sodium hydroxide is what? Well, it's calculated. What's sodium? We'll look it up. Sodium, 23.00. Oxygen is 16. Hydrogen is 1.01. So I get 40.01 grams per mole. Potassium chloride. Potassium, let's see, potassium's right here. 39.10. So potassium is 39.10, and I already know chlorine is 35.45. 35.45 for chlorine. Add together, you get 74.55. Grams per mole. Now we're starting off with 100 grams each, correct? 100 grams, 100 grams. So we're using Henry Ford, assembly line. We're doing the same thing over and over. Only for this one, we need 40.01. And for this one, we need 74.55. So that's the number of moles of each one. Four places. 2.499. And for the other one, 74.55. 1.341. Right? And they're in the same volume, right? So you can probably see by now that this one's going to be a lower molarity than that one. So how many liters is 250 milliliters? 3 to the right. Right? Move that decimal place over here. 0.2500. Yeah. And that will give you molarity. So let's do this one first. Is 5.366. Yeah, 4 significant figures. 5.366. And that one is 2.499 divided by 0.25 is 9.998. There you go. Well, round it off. They shouldn't have rounded that off, though, because you've got 4 significant figures here. That should be 9.998. And that one should be 366. Okay. New topic. All right, let's see. Yeah, we're good. Dilution. When I was working in soil sciences, we would do extractions of the soil with various types of solutions. And then we would filter the solution and analyze the solution for various, usually metals, but sometimes non-metals, cations, anions. But we would do hundreds of them, of these extractions. And we would need lots of solution. But we didn't have the time to wait to make up this huge batch of an extracting solution. So what we would do is we would make up a concentrated version, maybe 100 times or maybe 1,000 times more concentrated than we needed. And then when it's time to do the extractions, we would prepare fresh solutions from the concentrated version and go ahead. This is how you do it. It's a process called dilution. And this is a quantitative dilution, not just dumping extra solvent into a beaker and say, oh, I've diluted it. We need to know exactly the concentration of our diluted solution based upon the concentration of the concentrated solution, the volume that you use from the concentrated one, and the final volume of your diluted solution. Okay, so here's how you do it. The generic expression is the concentration of the stock solution, that's the concentrated one, times the volume of that stock that you extract and want to use, is equal to the concentration of the diluted solution times the new volume of the solution. Now, that theoretically will work with any of our concentration expressions, but I'm more interested in the one where we use molarity. So instead of C here, I use M for molarity. So the concentrated one here and the volume that you extract from it, then you dilute that to this volume and you get that molarity. Right? Sometimes we write it like this. So that we can tell the difference between concentrated and dilute. Now, why does that work? Right? You're just going to take my word for it? Why does it work? Well, with molarity, this is your concentrated solution. Right? There's your concentrated solution. What does M times V mean? Well, look at the expression. Molarity is moles per unit volume. So molarity times volume equals moles. This is equal to moles of the solute. Okay? So you put it in a container over here of a known volume, right? And you take out a volume here of the concentrated, and you put it in there. All right? What has changed between here and here? Nothing. You still got the same moles you got when you pulled them out here. Same number of moles over here. So this number of moles equals that number of moles. Right? And the expression for this one is moles times volume. Molarity times volume equals that number of moles over here. So the reason that these two are equal is because the moles are equal for both of them. Okay? So we got some problems to solve here. This dilution problem uses percent mass volume, right? It doesn't say. We have to assume from a previous problem that that's what it means. 0.9 grams per 100 milliliters. How would you make 100 milliliters of this concentration if your source was 10%? Right? So there's your formula. This is the stock solution, or the concentrated one, and this is the diluted one. So where do your values go? It's important, if you're reading a word problem, to extract information from the word problem and put it in mathematical form, right? So the concentration of the diluted one equals 0.9%. And the volume of the diluted one equals 100 milliliters. The concentrated of the stock solution is 10%. We want to know how much of the stock needs to be withdrawn. So each of these answers down here is so many milliliters of the 10% plus how many milliliters of water to make 100. Okay, first we need to know what volume do we need to extract. Once we know the volume we extract, then we know how much extra volume to add to reach the 100 milliliters. So we take this concentrated times this volume equals this diluted times this volume, and we find that the volume we need is 9 milliliters of stock. So to make 100 milliliters, we would add 91. Now that's assuming that the volumes are additive. And once you get something in solution like this, it usually is additive or very close to it. However, it would be better if you diluted 9 milliliters to a final volume of 100 milliliters. And how do you do that? Well, you need volumetric glassware. And most of them look like this. That's supposed to be a flask. A volumetric flask has a long, narrow neck up here, and it has a mark on it. And that mark tells you when you have exactly the stated volume there. Let's say this is a 100 milliliter volumetric flask. So that point will be 100 milliliters of solution contained in that flask at a different temperature, right? We know that liquids expand and contract with temperature, so you have to be mindful of the temperature. It's usually 20 degrees Celsius. So when you fill up your aqueous solution there, how do you know that you've got the right mark, right? If you've ever looked at a narrow tube with water in it, you notice that it forms a concave meniscus, right? Like that. So where do you measure it? On that line. Do you make the line right in the middle? Do you make it on the top? Or make it on the bottom? Well, by convention, aqueous solutions and these volumetric flasks are calibrated for aqueous. You match that line to the bottom of the meniscus. Okay, so when you do your dilution, it has to be at the bottom of that meniscus. All right. So what if you dissolve something, even if it was already in solution? Sometimes they either get cold or get hot. What if the temperature does change? what do? Well, you dilute up to right about here, and you mix it up well, and then you wait for it to come to room temperature. Once it's at room temperature, then you can finish diluting up to the mark. That way, you don't exceed or undershoot the mark. All right. So let's see. I'm probably going to run out of time, but that's okay. I'm recording it. And I shouldn't be too far behind. I still have some things that need to be discussed. So I'm going to get those in today. So a 0.50 molar solution of sodium chloride sits on a lab bench. Which of the following would decrease the concentration of the salt solution? How would you decrease the concentration? You can't add more sodium chloride and decrease. That would increase, right? How are you going to get the sodium chloride out of there if you want to decrease it? Not easily. The best way is to add solvent. Then you would decrease the concentration of the salt. So let's see. Add water to the solution. Yeah, that would work. Pour some of the solution down the sink. No, in a solution, the composition is the same throughout. So if you pour some of it out, the concentration is the same. Remember, concentration is an intensive property. Everywhere you look in that solution, it's the same concentration. So pouring some down the drain isn't going to do a bit of thing. It won't do anything. Add more sodium chloride. Well, no, we just said add more, that would increase the concentration. Maybe, unless it's already saturated. But 0.5 molar, it's not saturated. D, let the solution sit out on the open air for a couple of days. What would happen? Sodium chloride is not going to evaporate. Water is. That will concentrate the solution. It won't decrease the concentration. At least two of the above would decrease. Now, A is the only good answer. Add more solvent. How about this one? What is the minimum volume of a 2 molar sodium hydroxide solution needed to make 150 milliliters of a 0.8 molar sodium hydroxide solution? Okay, this is a before and after, and you need to put the terms in their proper place. So what is the minimum volume of a 2 molar sodium hydroxide? That's the concentrated version. So the molarity of the concentrated one is 2 molar. What's the final volume of the diluted solution? 150 milliliters. And what's the diluted concentration? 0.8 molar. So this is what we want to know. How much volume of that 2 molar solution do we need to dilute to 150 milliliters to make that concentration? Okay, so you know what the expression is. MC VC equals MD BD. We're going to solve for this one. And substitute our values. So MD is 0.800 molar. And then VD is 150 milliliters. And 2 molar on the bottom. Now, why didn't I change that to liters? Because this is a ratio. Notice if you have milliliters here, milliliters there, they cancel. So the volume doesn't have to be changed for this formula. It only has to be changed for the definition of molarity. But for this formula, you can leave it in milliliters here, and that way your answer will come out in milliliters. So let's see what it is. 0.8 times 150 divided by 2. 60. Three significant figures. 60.0 milliliters of the concentrated solution diluted to 150 milliliters will produce a 0.800 molar sodium hydroxide solution. Okay? I mean, if you want to, you can change it to liters, but you don't have to. The only time you need to change to liters is when you're using this formula. If you're using that formula, you have to change it to liters, because molarity is moles per liter. Moles per liter. You don't have any choice. All right. Now, I mentioned earlier that there was a class of mixture that had many of the characteristics of solutions, but it's not a solution. Colloidal dispersions are homogeneous mixtures. That is, they're uniform throughout. Concentration of the solute is the same everywhere. The difference is that the colloid is based solely on particle size. So the particle size is small enough for a colloid that it will remain suspended indefinitely. But it's not a solution because it did not undergo step 1, step 2, step 3 in the formation of our solution. We just made the particle sizes so small that the kinetic energy of the solvent and its molecules bouncing against the solute would keep it suspended. Now, I use those terms for a solution, and I shouldn't have, because the solute for a colloid is actually called a dispersed phase, and the solvent is called a dispersing medium, in order to distinguish between solution and colloid. 1 second. Okay. Do we know colloids? Except maybe we know them and we just don't recognize them as that. Well, there's an edible colloid. Goes by the brand name of Jello. It's a, once you prepare it, it's a mixture of gelatin and water, with, of course, sucrose and flavorings. Okay. Now, in this case, you've got both kinds. Gelatin in water is a colloid, but sucrose and these flavorings in water, they're solutions. So you have a combination there. Gelatin is a protein that's derived from primarily from animal parts, bones and hooves. It's extracted from those parts. So how do we tell the difference? There's a very simple way to tell the difference between a solution and a colloid. It's called the Tyndall effect, Tyndall effect. And it's based upon the difference between a solution and a colloid in terms of light scattering. For a solution, if you shine a beam of light, I got a little one here that I use in the laboratory, right here. If you shine a beam of light through a solution, you won't be able to see the beam unless you have a detector on the other side. It can detect the beam. Or if your eyes are over here, someone else is standing over there, they can see the beam. But you don't see it going through the solution. In this case, the atmosphere is a solution of nitrogen and oxygen primarily. I don't see the beam. When would I see the beam? If there are little particles floating around in it. You could see those. They would scatter the light, and I could detect it. Well, the same thing happens in a liquid solution, like water. If you shine the beam through a liquid solution, you will not see the beam go through. You detect it on the other side, but not in the solution. It will not scatter light. Whereas in a colloid, when the light passes through the colloid, through the colloid, you will be able to see the track of the beam. Okay, and the next slide gives you an example of that. So this first one is a solution. Notice you can't see the beam in here at all. You can see reflections off the glass, but not in the solution. Then when you reach the colloid on the other side, the light is scattered, right? So this is a solution, this is a colloid, a colloidal dispersion. And we use that in the lab when we're doing, let's see, we don't do that one in this class. There's a particular titration where you add certain amounts of chloride to a solution and you precipitate silver chloride. Well, silver chloride is, if it's concentrated enough, there's enough of them in solution, then it has an opalescent, it's sort of a shimmering effect. But it takes a lot more than you need to reach the endpoint of your titration. So in order to detect the endpoint more efficiently, one of the students will take that light and shine it through the receiving vessel so that you can actually see when the silver chloride forms, because it is a colloid. And not strictly speaking a colloid, because if you wait long enough, that silver chloride will settle out. So it's a suspension. But the Tyndall effect still works because there's light scattering. Okay. So we go from a solution to a colloid where the particle size is small enough for the dispersed medium to remain suspended. And then we talk about suspensions. So a colloid is kind of in between. A true suspension is it's a heterogeneous mixture, which means every part of the mixture has a different composition, a different amount of solute for the size of the solvent sampled. And the other thing that happens is in a suspension, eventually the suspended medium will settle out under the force of gravity. If it's a solid, if it happens to be a liquid like vinegar and oil, mix those up really good. Well, in that case, what we would associate with a solute, but it's not called a solute, the suspended medium, the oil, will float to the top, but there is separation eventually, physical separation of the two. Okay, so here's a side-by-side comparison. Types of mixtures: a solution and a colloidal dispersion are both homogeneous. Suspension is not. What types of particles in a solution? You could have atoms, ions, or small intact molecules. Colloidal dispersions have groups of small particles or individual larger molecules. So it can be a molecule, but it doesn't have to be. It could be just a finely divided something, compound. Not individual molecules necessarily. A suspension, very large particles, and they're very often visible to the naked eye. The effect of light. Solutions are always transparent. Colloidal dispersions are will disperse light with the Tyndall effect. And I take issue here with suspension. Not transparent. Some suspensions are transparent or at the very least translucent and will respond to a Tyndall effect if they're dilute. All right. So there's a qualifier for that one. Settling properties. Solutions never settle. Colloidal dispersions never settle. Suspensions settle, sometimes very rapidly. If it's a solid is in suspension. If it happens to be a less dense liquid in suspension, it'll rise to the top. So there's another issue I take with that one. How about filtration properties? When you filter a solution, you get nothing. Right? Those particles pass through with the solvent. Colloidal dispersions. Generally speaking, those cannot be filtered out either. They're just too small. Theoretically, you could form a filter medium that had a small enough pore size to remove the colloidal, the dispersed medium. But in general terms, you can't filter them. But suspensions, yes, always. You just need to choose the right filter medium to get those solid particles out. Okay. So there's a colloidal dispersion is all three of these. I'll let you read those at your leisure. Now, I'm right at the point, and we need to discuss colligative properties. These are extremely important and useful properties, physical properties of mixtures. Okay, and we're going to talk about 4 different ones. Lowering of vapor pressure. So what do we mean by that? If you have a liquid with a definite vapor pressure, then if you add a non-volatile solute to that liquid, the vapor pressure will be lowered, right? And it follows a definite law called Raoult's law. Elevation to boiling point. If you have, say, water that normally boils at around 100 degrees, well, at this altitude it's less. But if you add anything to it that goes into solution, like sodium chloride, in aqueous solution, or actually in any kind of solvent, once you form the solution, the boiling point of the solution then is higher than the boiling point of the pure compound. And that follows also a law. Depression of freezing point. Take that same solution and try to freeze it, and it will freeze at a lower temperature than the pure solvent. Osmotic pressure. We have to define what osmotic pressure is, so I'm going to skip this one for now and talk about it later. Let's talk about vapor pressure. This is Raoult's law, and it relates the vapor pressure of the solution to the vapor pressure of the pure solvent. And the factor is this, X of the solvent. What is X? X is the mole fraction. And it's very simple. The mole fraction, often written like that, is simply the moles of solute divided by total moles of the solution. So if you only have two, one solute and one solvent, then you would add the moles of solute to the moles of solvent, and that would be your total. If you have more than one solute, then you just add them all up to make the total. But it's a fraction. It is a fraction, and it will be less than 1. Right? And if you add up all of the mole fractions for every solute in the solvent, they will all add up to 1. So that's what mole fraction is. It's the fraction of moles. And this is the factor that determines the vapor pressure lowering. In other words, if this is the vapor pressure of the pure solvent, this is the mole fraction of the solvent. Excuse me, I made that mistake. This is true, the mole fraction of the solute, but the mole fraction of the solvent is what we want for Rayleigh law. In that case, it would be moles of solvent divided by total moles. Okay, that's important. So don't make the mistake I did. It needs to be the mole fraction of the solvent. So the mole fraction of the solvent decreases as you add more solute, which means the factor is less than 1. So the vapor pressure of the solution is now going to be less than the vapor pressure of the solvent. That's what this little 0 is. That means the pure solvent. So why does that happen? Well, notice before, the vapor pressure is based upon how many molecules of the solvent escape into the vapor phase. And if this vessel is closed, it will build up a pressure at a given temperature for the solvent. And you can measure it. If you add solute to it, what happens? Well, two things happen. One is you obscure this interface between the liquid and the gas phase. So now fewer molecules of the solvent have an opportunity to escape. They're blocked, physically blocked by the presence of the solute. But there's one other factor that may be involved, and that is intermolecular forces. Perhaps the solvent and the solute are attracted to one another, and that attraction restricts the escape of solvent into the vapor phase. So those two factors together will decrease the vapor pressure of the solvent. Actually, decrease the vapor pressure of the solution as compared to the pure solvent. Okay, boiling point elevation. Boiling point elevation is a measure of temperature difference. Right? Temperature difference. And for using this formula and the next one for freezing point depression, the delta T is the absolute value of the difference. So this is the temperature, say, of the pure solvent minus the temperature, actually the boiling point, and the boiling point of the solution. Now, why did I say absolute value? Because we already know that it's a calculation for a boiling point elevation, right? So this difference in temperature is going to be added to the pure boiling point to get the new boiling point. But the calculation itself is just the difference in the temperature. Okay? And the That's the first thing. The second thing is this constant value is different for every solvent. So water will have one, ethanol will have one, carbon tetrachloride will have one. So that is different for each pure solvent. This value is new. This expression of concentration is new. We haven't talked about it yet. It's called molality. Molality is like molarity in that you have moles of solute, but instead of being divided by liters of solution, it's divided by kilograms of solvent. Okay, moles of solute per kilogram of solvent. Now, why do we need that? Why can't we use molarity? Well, notice we're interested in a temperature change. So what happens to concentration when the temperature changes? If our expression is moles per unit volume, if we increase the temperature, the volume is going to increase, which will change the concentration. And we can't have that. The concentration needs to remain, needs to be a value that we can depend upon. And if we use mass down here instead of volume, now it's fixed. It's always that no matter what the temperature is. Okay, so that's molality. Now, one thing that I forgot to do is explain what is a colligative property. A colligative property is one which does not depend upon the identity of the solute. Okay, each of these properties is independent of the chemical nature of the solute, which is good because now we can use a colligative property to determine molar mass of an unknown compound. We don't need to know what the compound is. We can still get its molar mass by using one of these colligative properties. Okay, so back to the topic. The K value usually has units of, in this case, for water, K for water, boiling point elevation, for water, constant, is 0.51 degrees C for every molal. So if you increase the molal concentration of your solute by 1 unit, you will get an increase in the boiling point of 0.5 degree Celsius. Sometimes we need to use this for other calculations. So we need to know, what does molal mean? Well, if molal means moles per kilogram, then this also means 0.51 degrees C times kilogram over mole. Same thing. Remember, denominator of the denominator is the numerator. So this one comes up here on top, this one stays on the bottom. That's also a useful set of units for this value. Now, these values are determined for standard temperature and pressure and standard concentration. Now, they have wide application because they're reasonably fixed for a broad range, but it may be necessary if the value of temperature or concentration is extreme. You may need a modified K to do the calculation. So what's standard temperature? Well, unlike gases, gases' standard temperature is 0 degrees Celsius. For anything else, it's 25 degrees Celsius. Pressure is the same, 1 atmosphere. And for solutions, the standard concentration is 1 molar. Right, so that seems kind of weird, doesn't it? You're using molal for the calculation, but the standard concentration is 1 molar. Well, if the solution is fairly dilute and the temperature is 25 degrees, 1 molal equals 1 molar. Why? Because 1 kilogram of solvent, which is water, is also 1,000 milliliters, or 1 liter. So that's why 1 molal equals 1 molar under these restricted conditions. All right, freezing point depression. This one is similar. But now with the calculation, you have to recognize that this absolute, let's see, let's change that. Now this is freezing point. Now the absolute change in temperature is a depression in the freezing point. So if water freezes at 0 degrees Celsius and you add enough salt to it, it will now freeze at a much lower temperature. That's the whole operating principle for ice cream freezers. You add salt to ice, you get an ice-water mixture, and as long as you have that mixture with the salt in there in the solution, then the freezing point is going to be dropped. And it may go down to -20, -15 or -20 degrees Celsius to freeze your ice cream. The value for water, this K value for water, and we use molality again. The K value for water in this case is 1.86 degrees Celsius per molal. All right. So if we add a non-volatile solute to a solvent, how does that affect the vapor pressure? It decreases the vapor pressure. And the next colligative property, osmosis. I think we have a lab that uses this one. Osmosis and Dialysis is the lab. Osmosis is the term that describes the passage of a solvent, and for living systems that's water, through a semi-permeable membrane that separates two solutions. One solution is more concentrated than the other. Right? So if you have a membrane here, and you have a dilute solution here, and a more concentrated solution here, the only thing that can pass through that membrane is the solvent molecule. And for a semi-permeable membrane, that's water. Right? So nothing on this side can get to that side except water. But which way does water want to move? Well, think about concentrations. On this side, what do we mean by dilute? That means low, you know the marker. That means low solute concentration and high solvent concentration. In this case, water. Okay? On this side, we have high solute concentration and low solvent concentration. Okay, so to determine the water movement, we need to say, all right, if we're going to say what moves through that membrane is water, then we need to focus on the concentration of water. Water will move from, well, actually, any compound that can pass through the membrane would move from high concentration to low concentration. That's just the way things happen. In this case, water is high on this side and low on that side, so water moves this way. Right? In that case, it increases the solute concentration on this side and decreases the solute concentration on this side. Okay? Now, there's another type of membrane called selectively permeable membrane. In selectively permeable membranes, other things besides water will pass. And it's based upon the size of the molecule and the pore size in the membrane. If the pore size, and the pore size can be adjusted very accurately to pass small molecules, right? So maybe glucose will be allowed to pass, but starch will not. Starch is a huge molecule. Glucose is a small molecule. So in a selectively permeable, we might be able to get glucose to pass. And it depends on which side is the higher concentration of glucose. If it's higher on this side, it'll move that way. Okay? But for semi-permeable membranes, we're talking about water. That's the movement. So what happens if this container is sealed, right, against all movement of gases and liquids and solids? Well, as water moves over here, let's say we have a little headspace up here. The solutions are down here. The water moves this way. What happens to the pressure up there? Well, it increases, right? Because as you move water this way, the volume goes up. And if the volume increases, then the pressure in that trapped gas is going to increase. That's Boyle's law. Volume decreases, pressure increases. That increase in pressure is known as osmotic pressure. Now, that's one way to express it. There are other ways to measure and express osmotic pressure. Here's another example. Instead of being sealed, we actually have an open tube here. So our concentrated solution is inside the tube, and here's our semi-permeable membrane, and there's our dilute solution. So which side has more concentrated water? The dilute solution, which moves through the membrane into the concentrated solution. And it continues to move, and as the volume increases, we get that rise in height. So when does it stop? It stops when the pressure difference between this surface and that height, that pressure difference there, is equal to the force that's driving water into the tube. That's when you reach equilibrium. Now, the concentrations inside and outside don't have to be equal at that point. What we're talking about now is the equivalence of pressure. The pressure driving water into is equal to the pressure driving water out of. And it's based upon this difference in height. So that height supplies the pressure. All right. So this is their artist rendition of what happens at the microscopic level for a semi-permeable membrane. You see the water molecules moving right across the membrane. So some clever scientist or engineer took this concept of osmotic pressure and said, okay, what if we have a concentrated solution in here and we artificially increase the pressure on it? We just magnify the force against there. What's going to happen? Well, in that case, water is going to move from the concentrated side to the dilute side. We have, by applying this pressure, we have exceeded the baseline osmotic pressure between the two solutions. This is called reverse osmosis. And it's the basis of most desalination plants on the planet. You take salt water and you apply enormous pressure to it, and that drives water through the semi-permeable membrane, leaving the salt behind. And at the end of the process, you have an enriched brine that is sent somewhere else. It's either dumped back in the ocean or the body of water, or it's shuttled away to do something else. Okay, let's see. There was one topic, osmotic pressure. Oh, okay, before I get to that one, let's talk about osmolarity. If, and we actually have to introduce the topic, actually there's kind of backwards. All right, let me take it as is, and we'll pull them together afterwards. And then we'll go back to the slide with the tree. I want to talk about that. In order to compare one solution with the other one, we needed an expression of comparability. And the problem is, if you're comparing two solutions, the osmotic pressure depends upon the number of particles in solution, not on the number of molecules. So if we say we have sodium chloride in solution, right, in aqueous solution, and it's a 0.1 molar, how many particles do we actually have in that solution as far as the osmosis goes? Osmosis cares about the total moles of particles. So we actually have 0.2 molar ions. Okay, so for that reason, if the molecule dissociates, then we need to take its molarity and multiply by the factor. This factor is usually the number of particles from which the unit is derived. So in the case of sodium chloride, the I would be 2. So 2 times this would be not molarity, well, it'd be molarity of ions, but it would be a 0.2 osmolal solution. The problem is that in actuality, in solution, some of those sodium and chloride ions come back together, and they're actually intact, dissolved in water. So the value of I would be somewhat less than 2. And that has to be experimentally determined. But theoretically speaking, I equals 2 for sodium chloride. For, let's see, what else could be dissolved? Calcium chloride, I would be equal to 3. For sodium phosphate, I would be equal to 4, because you would have 1 of these and 3 of those. So you have 4. So what's the osmolarity? I said osmolality, I meant osmolarity. Osmolarity of 3 molar sodium chloride would be 2 times 3 would be 6, right? So it's 6 osmolar. Okay, let's talk about tonicity. Any one of my students that has been exposed to the medical profession understands hypotonic, isotonic, and hypertonic. But this is what they mean. They have a practical understanding. The solution with the lower osmotic pressure is hypotonic. And we generally refer to hypotonic with respect to intact cells, like it would be in your body. So a solution that's hypotonic to your cells has a lower concentration of solute than is in your cells. Right? So what happens to the cell? There's your cell. If the solution is hypotonic, right, with a lower concentration of solute, meaning a lower osmotic pressure, that means you've got a higher concentration of water. So the water is going to move into the cell. And if the hypotonic solution is the difference between concentrations is high enough, the cell will rupture. And of course, if you're giving a hypotonic solution to a patient intravenously, the first thing that's going to rupture is blood cells. They will swell and explode. If you were to inject pure distilled water into your patient, you could probably be charged with murder because it would kill them. So that's a hypotonic solution. Before we get to that one, let's see, is the next one? Yeah, isotonic. Okay, so hypertonic would be hypertonic solution would be low water concentration or high solute concentration, which gives it a higher osmotic pressure. So the osmotic pressure is referenced to the concentrated solution or the solution inside the tube. Okay. If the concentration of water is lower than the outside of the cell, the water would move out of the cell. And in that case, the cell would crenulate, they say. It crinkles because you're decreasing the volume inside, and the membrane has a certain surface area, so to maintain, it has to crinkle. And you can see that under the microscope. If you add concentrated sodium chloride solution to a cell on your slide, and the cells are there, you can see them shrivel up. Inject that into your patient, you kill them too. It just completely destroys their red blood cells, among others. All right, so what's the ideal? The ideal is the isotonic solution. ISO. Iso means same. So that means the tonicity of the solution inside the cell is the same as outside the cell. Right? So if you use that type of solution to inject into your patient, then it will not damage the cells based upon tonicity. Now, there are certain solutions you don't want to inject in your patient for extended periods, I should say. You saw earlier 0.9% sodium chloride is isotonic to human tissues. The problem is it pumps your system full of sodium and chlorine if you use just that solution, right? Your kidneys can get rid of a certain amount of sodium and a certain amount of chlorine efficiently, but if you put too much in there, it'll cause kidney failure, right? So that's why various other isotonic solutions have been devised, like the most common that I know of is lactated ringers solution. So it has a mixture of other types of solutes in there that do not put the same kind of pressure on your liver and kidneys that a pure sodium chloride solution would. But this lactated ringers is isotonic to your tissues. And it's often used as a transport medium for other drug deliveries. So you might have a ringer solution where they're trying to replenish your body fluids, you're dehydrated, but you also might have an infection. So they have a little side bag going into the stream with an antibiotic. Okay, so let's see. Okay, here's a slide. So this is this cell has been immersed in a hypotonic solution. It's imbibed water. This one's in a hypertonic solution. It's crenellated. And this one's in an isotonic solution. Looks like a normal blood cell. So 5% mass volume of glucose is isotonic to your tissues. And it's often listed as D5W. D stands for dextrose, which is usually glucose, but it doesn't have to be. Any 6-carbon sugar will be a dextrose, and it could be a mixture. But it's 5% weight volume. That's what D5W means. But if we convert the glucose, convert this unit of measure into molality, osmolarity, we come out with 0.2775 is the osmolar concentration of anything. So that ringer solution, the 0.9% sodium chloride, 5% glucose, they are all very close to 0.2775 osmolar. Okay. Let me go back to the tree. Yeah. So these are sequoias. Sequoia gigantea is a scientific name for these trees. There are several sequoias over there, but I think this is probably the gigantea. You see this guy standing down here, so you can see how big those trees are. Well, they're very tall. Some of them up to 300 feet, 350 feet tall. The problem with that is that how do you get water to the top? Right? You can't do it with a vacuum. In other words, if you have a vacuum above a column of water, like like this. So that's water. And you have this tube, and you have a vacuum at the top, right? You got 1 atmosphere pressure here, right? So how high would that water rise in the tube with 1 atmosphere and nothing pressing against it here? About 33 feet. Is as high as you can get it. So that's why scuba divers say for every 33 feet that you descend, you add an extra 1 atmosphere pressure as you go down. Anyway, so a tree any taller than 33 feet can't get water to the top based on this principle. But we know that water does make it to the top of these trees. So how does it do that? Well, it can't be from a pull, because if we pull with a vacuum, that's not enough. So it needs to be a push. So here's how it pushes. Dissolved substances in the tree sap create a more concentrated solution than the surrounding groundwater, right? So the groundwater is hypotonic to the tree roots, which means what? Water is going to move into the tree roots. And depending on the difference between the groundwater concentration and the sap concentration in the tree, you get that differential of osmotic pressure, which obviously is enough pressure to drive the water all the way to the top of the tree. So that pressure in the roots can exceed 20 atmospheres. It's been measured. So if we know that that difference is 20 atmospheres, this is the osmotic pressure in the tree roots. Is it enough for water to reach 300 feet high? So that's what this calculation does. So 300 feet translates into 9.144 times 10 to the 4th millimeters tall in the tree. All right. So then we take, that's how high the water has to move. So with 20 atmospheres, that's 760 millimeters of mercury per atmosphere. Then 20 times that would be millimeters of mercury high, but water is less dense, 13.56 millimeters of water for each millimeter of mercury, right? So we find that we can push the water up to 2 times 10 to the 5th millimeters, right? So that's far in excess of the pressure needed to reach the top of the tree. Okay. So let's skip back over to, let's see, here we are. We were at this slide, I believe. Characteristics of, let's see. Yeah, I'm about 40 minutes past. Characteristics of hypotonic, hypertonic, and isotonic solutions. This is just gathered together. I said earlier, this solution is 0.2775 osmolar. The 0.9% sodium chloride solution is actually a little bit more concentrated than that, 0.308. Right, so that's a ballpark figure. The problem, of course, is sodium by mass is, well, the physiological overload to your system is, in this solution, would be 10% overload compared to drinking pure water. And chloride would be even worse than that, 50% overload to your system. And here's the article that I cite for those statistics. If you want to read it, it's right there. So what's an isotonic solution? That's where the osmotic pressure is equal on both sides of the membrane. In this case, a cell. How do we determine the osmolarity of the solution? Well, you multiply the molarity by the number of particles that are produced per unit, per formula unit of the solute. All right, let's see. Is this going to help us any? How would you prepare 200 milliliters of 0.8 molar sodium hydroxide, molar mass 40 grams, in water? All right. So we need 200 milliliters final volume. And molarity is 0.8. Oh, excuse me. And the molarity we want is 0.8 molar. And this is for sodium hydroxide in aqueous solution. Okay? So we're given 40 grams per mole as the molar mass of sodium hydroxide. So we need to know, based on this formula, we can tell how many moles is required. So moles is equal to molarity times volume, which is equal to 0.8 times what volume? 0.2 liters. Okay? So this gives us the number of moles required. 1.6 times 10 to the minus 1, or 0.16. 0.160 moles. So 0.160 moles. And dimensional analysis tells us that moles on the bottom, grams on the top. So 40. And that's equal to 6.4 grams of sodium chloride in what? In a final volume in 200 milliliters of solution. Okay? Did I do that right? Yeah, 6.4. 6.4 grams actually, neither one of these is right. Add that much to 200 milliliters of water. The solvent is water and the solute is sodium hydroxide. Yeah, that's probably the one. Dilute 200 milliliters of water. So you're not actually adding it to 200 milliliters of water. You're adding it to some water, then you're diluting to 200 milliliters. And I might caution, if you're adding sodium hydroxide to water, you want to have sufficient water, 150, 160, or 70 milliliters when you add the sodium hydroxide, because that reaction is extremely exothermic. If you put that water, say you put 50 milliliters in a plastic beaker and add this sodium hydroxide to it, it will melt the beaker. So put it in sufficient amount of water to dissolve it, and then let it cool to room temperature. Then finish diluting to 200 milliliters. It's the old adage, when you dilute a strong acid or a strong base, the safety rule is do as you oughta. add acid to water. Do as you ought to, add acid to water. In other words, you add a small amount of acid to a large amount of water, and for bases also, but that doesn't rhyme as well. Add base to water. Okay, you could do that because the heat of solution is extremely exothermic. And if you add it to a small amount of water, what it may do is be so hot it could boil instantly, and it would spatter. Okay. So let's see, are there any others? That was concept. There's usually 2 concept questions. Yeah, here's another one. If you add 2.6 grams of sodium chloride, molar mass 50, to 300 milliliters of water, what's the molarity? The percent mass volume and the osmolarity of this solution. So we got to do 3 calculations. Right? Let's see, I think I've done those, haven't I? No, I didn't do them. Oh, all right. So let's do them. So you have a mass equals 2.6 grams of sodium chloride. And you have a molar mass of 58 grams per mole. Okay? And your final volume is 300. Okay, that's everything we're given. And the question is, what is the molarity, percent mass volume, and osmolarity? Well, percent mass volume is easier to calculate right now because we have the values we need. So the mass, percent mass volume equals the mass of the solute divided by the volume. And we have to assume that the final volume is going to be 300 milliliters. Right. Now, that is mass per volume times 100. The only reason we can do that reliably is because a gram of water is a milliliter. So the mass percent should be very close to the mass volume percent for this reaction, for this solution. So let's calculate it. 2.6, 300 divided 100 times is 2 significant figures. 0.87. Okay. Okay, now how about molarity? Molarity, you need the moles of sodium chloride. So this many grams divided by 58 equals what? Is 4.48 times 10 to the minus 2. Okay, so the molarity now is going to be that value, moles per liter, 0.3 liters. I get 0.149. Okay. How about the osmolarity? Sodium chloride breaks up into 2 ions, so the I value is 2, and the osmolarity is 0.300. Okay, so in the order that it's asked, molarity, percent, and osmolarity. So molarity is 0.149, 0.15, they rounded it off. And then this one is also rounded off to 0.87, 0.9, and then 0.3. So A has to be the answer. Okay, I think that's the last slide. And I'm all alone, so there won't be any questions. And we'll stop the share and just say that next Friday, which will be the 16th, we will do a review of Chapter 7 and Chapter 8. I'm not sure how I'll do it yet, but if you have any questions, work those homework problems. And if you have any questions on the homework problems, bring them to class so that we can straighten things out. And I'll try to prepare for a dead air and fill it in with reviewing the topics that I think are most important, so for your success during the exam. All right, that's it for today.